Now, he's looking for the definition of Kelvin here. Anyways, I'll say it. So the thing about Kelvin, come on. Hang on. Did I what? Downgrade? No, I have to find the old package. There we go. The thing about Kelvin is it's an absolute scale. So for the marks here, they want to see words like absolute, and absolute meaning that it starts at 0. Okay. So the first thing here, A part 1. I won't write the full story, yes. I'll just give bullet points. So what they want to see is they want you to see, to use the word, I think they want absolute, yeah. Absolute scale, which means that it starts at 0. That 0 Kelvin is well, I suppose we'd call it absolute 0. And what's special about this state is that it's not minimum kinetic energy. What's special about absolute 0? There's no kinetic energy of the particles. And finally, he wants a second point on the Kelvin scale. So what would be another point to use? Well, the normal one to use is 273.15 degrees Kelvin. And what does that represent?
0.
Yeah, which is what's special about 0. What is so special about 0 Celsius? Yeah. Now, there's a special name for that. It's called the triple point. Sorry, there's only one P in triple. Triple point. But as you said, KJ, it's the freezing point of water. But I mean, it's a bit more complicated than that. But I think if you actually said freezing point of water, I don't know if I'd still give you the marks. He's particular here. We have to say triple point. Triple point is not only the freezing point of water, but that's part of it. I didn't actually say what the triple point was in class because it's not really something on the course. But you know the word now. Just think about triple point as like freezing point of water, but it's also other things as well. Hence why it's called triple point. You could probably guess how many special features? 3, yeah. So the fact that water freezes at this temperature is just one of the 3. Okay. Right, what happens? Oh, I accidentally did the second part. What happens to the energy at absolute 0? Yeah, I just did it there. How does the energy change as the temperature increases?
It increases.
Yeah, so the change in the energy is positive as the kinetic energy increases. In a real gas, the internal energy depends on the kinetic and the potential. Explain why this is not the case in an ideal gas. So you remember from the proof, that's bad. Sorted? Okay. So if you remember when we did the proof for the ideal gas law, we said that why don't you sit over there, because you're in front of Carrar. Can you still see? Are you sure?
Yeah.
Okay. If you remember from the proof, we said that at the start we assumed that there's no potential energy for an ideal gas. So anyways, why is this not the case in the ideal gas? So actually, the definition of an ideal gas means that there's no interacting force, only collisions. And no interacting force means no potential energy. And that's it. I wonder what it says here. Yeah. How does an ideal gas, so again, if you remember the proof, if you remember in this lesson I said you don't need the proof in the exam, but I did say I'm doing it because parts or understanding of the proof is tested. So this is a good example of what I was saying. How is an ideal gas able to exert a pressure on the wall? So in other words, with the ideal gas, how does it make a pressure on the wall? By colliding with the wall. So what happens is, as the molecule comes in, its speed is v, and then after the collision it's minus v. So the impulse, the change in momentum, is minus mv minus mv. That's minus 2mv. So that means the force equals minus 2mv if, for example, the time is 1 second. But force, pressure is force over area. So basically, therefore, the force to change direction is what causes the pressure. That's the force the wall exerts on the molecule, and likewise the force the molecule exerts on the wall. This here is what causes the pressure. So the marking scheme answer is actually, I think, probably less technical than this. It says, pressure is caused by the fast moving atoms colliding with the wall of the container. If you gave me that, I'll happily give you the 2 marks. You deserved it. Okay, so that's the A part of B3. So far we have 1, 2, 3, 4, 5, 6, 7, 8 marks really just for definitions. And not too difficult, I don't think. Right, B. So now this is a gas. The volume is 32.6 times 10 to the minus 3. The temperature is 25. The pressure is 2.36. And it's so easy. The first thing is that the volume is reduced to 1.25 times 10 to the 5. And what has happened to the pressure? So what's the relationship between pressure and volume? P is proportional to 1 over V. So what has happened to the pressure? It went from 2.36 10 to the 5 to 1.25. So what's happened to the pressure? Has it increased or decreased? Decreased. And how much has it decreased by? It's decreased by 53%. So the decrease here was by multiplied by 0.5297. That's how much smaller it is. Originally it was this, and now it is this. Just a division. So what happens to the pressure? It increases. So the pressure. Oh, sorry. Sorry. I'm looking at the wrong. No. Bad. Let's start that again. The volume changes. So what's the volume at the start? 32.6 times 10 to the minus 3, and then the volume afterwards is Oh my goodness! I was right the first time. The pressure, 2.36 times 10 to the 5 becomes 1.25 times 10 to the 5. This is like multiplying by 0.5297. So the volume, will it get bigger or smaller? Remember, the relationship is like this. Will the volume get bigger or smaller?
Small.
Bigger.
Bigger.
By how much?
By 50.
By dividing by this amount.
We're doing the second part now?
No, B part 1, yeah. So it's now 61.5 times 10 to the 5 pascals. Meters cubed. And their answer is... Yeah. What? Huh. No, their answer has to be... Oh, that is a -3 here. I should have written -3 here in my answer. Okay, now it's right. Okay, B part 2. What is the volume if the temperature is 0, the pressure is 1.01 pascals? Do we know the number of moles? No. We know the... do we know the volume? No, that's what they want.
Is that
So,
6?
part 2.
No, is that 10 power 6?
It is 10 power 5. Oh dear. Right, 10 power 5. Isn't it? Yeah. Okay. So if you look here, this is an example where it's actually easier to do the next part first, because the next part is to calculate the n. So I'm going to do that first, okay? PV equals n RT, so n equals PV over RT. Now we should use the numbers from the last part, because the n is not going to change unless they release some of the gas. So in the last part, what was the pressure? Or at the beginning?
In the beginning.
The very beginning, the pressure was 2.36. And the volume was 32.6.
Why are you not using the ones changed?
Say again? Why don't I use what?
The ones changed too.
But it doesn't matter, because the n is constant for the whole question, it's not changing. The R is 8.31 and the temperature is 273 plus 25. So I should get an n here.
3.11.
You sure?
No.
You're right. 3.11 moles. So now I can use that here and get the V. So you have V equals nRT over P. That will be 3.11 times 8.31 times 275 over 1.01 times 10 to the 5. Wait, no, not 275. 273, isn't it?
236.
No, the
What's that?
Kelvin.
Oh, 273.
273, not 275. Okay, 273 over 0.0699 meters cubed. Yeah.
If in the exam,
Yeah?
like we did, for example, we did the second part.
Yeah, you can do that first.
No, we did the third part in it, and then we just know like then the next one they ask different numbers. You can just write the answer. If there's calculation like available.
Suppose you could say C part 2.
No.
No, I understand what you're asking me. So you want to know if you do this part as part of part 2, then in part 3, can you just write the answer? And I just said you should write C part 2. And then you said no. So what don't you like about my answer?
This is in which
So in the exam you would say answer equals blah, and then in brackets C part blah. That's what I mean. Are you happy? Well, okay. Maybe not happy, but we're cool. Right. Part 4 is the number of molecules. So how do I get that?
multiplied by Avogadro.
Yeah. So what's Avogadro now? 6.02 times 10. 23. So this is 1.87 times 10 to the 24 molecules. And finally, what is the density of chlorine gas in the sample if each molecule contains 2 atoms? The relative atomic mass of chlorine is 35.5. So that means that 1 mole is equal to 35.5 grams. Yeah? How many atoms of chlorine do we have? Yeah, which is what? No, hang on, you're not thinking. We have 2 times 1.87 times 10 to the 24 molecules of chlorine. Do we not? Atoms, I mean to say. Because this is how many molecules of chlorine we have, right? But they say in the question chlorine appears in pairs. So the number of atoms is actually twice this. This is equal to 35.5 grams. So then the mass of 1 atom of chlorine is 0.0355 over 2 times 1.87 times 10 to the 24. The mass of 1 chlorine atom. No, wait. Determine the... Oh no, I don't even... I'm doing too much. Wait, I'm doing way too much. Retreat! Okay. I misread. They don't want the density of 1 chlorine atom. They want the density of the gas. So, what's the formula for density? M over V. Do we know the volume of the gas?
Yes.
Yeah, it was the answer from earlier. What was it? 0.0699. Now, do we know the mass of the gas?
Yes.
Well, we kind of do. We know how much 1 mole is. 0.0355. And how many moles do we have? No, it was 3.11, wasn't it? But we have to read the question very carefully because we're not sure if we should multiply it by 2 or not. So I don't know if this was the mass. See, I think that's actually the mass for...
multiplied by 3.11.
That's how many moles I have, isn't it? Wasn't it 3.11? Yeah.
But it said mass, not mole.
No, I know.
And is more.
Yeah, I'm getting the mass of the gas. We have 3.11 moles of gas, and each mole is 35 grams. So what's the mass of the gas? Yeah. However, I'm not sure if I should multiply by 2 because I think this is the mass for 1 chlorine. You see it here? So they...
No. Yes, multiplied by 2.
yeah, I think I should multiply by 2 because the chlorine is in pairs. So each molecule is actually 2 chlorine atoms, so I should multiply by 2. Let's check actually the marking scheme. Yes, multiply by 2. 0.0355 times 3.11 times 2 over 0.0699, and you get the correct answer. I think that was actually a good question. You know, I mean, how many formulas did you need to use for this question?
2, 3.
Well, really only one. PV equals nRT. You know?
And density formula.
I barely count that as a formula. Yeah, density, that's more of a definition of density. Yeah, okay. Let's have a look at 4 now. Have a read of 4. We'll do it now.